All right, so we've talked about how solids behave whenever you push or pull on them and whenever you change their temperature. And then we actually found out that it's the same for liquids as for solids when you change their temperature. They expand or they contract. And that left us with the question of what happens when you push on a fluid? Well, you can imagine having a bucket of water and sticking your hand down in it. You might think nothing much happens. It just gets out of the way, right? Your hand goes in, the water flows around it. Well, there actually is something going on there, and we'll get to that in a minute. But first, let's imagine if you sort of trapped that liquid. Let's imagine you have, say, some sort of cylinder filled with fluid, and you've got some sort of cap to place right on top of it. And that cylinder is connected to another cylinder that's different, but it's also got a cap that can seal it off, so we can really trap this liquid and squeeze it. Well, what's going to happen? So let's imagine we have this area A1 on the left-hand side, and we push down with some force F1. Well, that results in a pressure. Pressure is force applied to an area. P for pressure is just F divided by A. And if we want to think about the units for pressure, the units of pressure are the units of F, units of force divided by the units of area, which is going to be newtons per square meter. Newtons per square meter, or you might be more familiar with something like pounds per square inch, is a measure of pressure. And it turns out there's actually a special name for that, the Pascal. 1 Newton per square meter is referred to as 1 Pascal, which is abbreviated as PA, capital P, lowercase a, for pascals, which just means Newton per square meter. But back to our setup here. So what happens whenever you push on this water? Well, you push on the water, it pushes on all its neighboring water particles, and that pressure that you applied, the amount of force divided by the amount of area you applied it to, gets distributed all throughout the liquid. The water at the top pushes on the water below it, pushes on the water below it, it pushes on the walls, it pushes on the water through this connecting tube all the way over to this side, and then that water, it's still pushing upwards on that second area. But the amount of pressure, P1, is equal throughout the entire thing. So the amount of pressure on this area over to here, P2, is the same as the initial pressure from that area. Pressure P1 equals pressure P2, or using our definition of pressure as force over area, we can see that F1 over A1 equals F2 over A2. And I like to refer to this as the hydraulic equation. What we've essentially drawn here is a hydraulic lift. And we can exploit this, we can exploit these principles to make work easier. In fact, with the right setup, it can take minuscule, tiny amounts of force on an input piston to lift massive amounts of weight, massive amounts of force on the output piston. And the trick is to make the input piston very small, a very small area. You divide by a small number, a small area, it makes the overall number very big. You divide by a small area, you get a big pressure. Well, if we've got a big pressure and a large area, we need a large force. And so you actually get a very large force out of your second area, if it is bigger than your first area. And we'll work some examples to see that in action, of course. One last note on pressure is atmospheric pressure. I wanted to talk about this because I don't know if you guys know, but you're being pushed on right now. Pushed pretty hard, in fact, too. There's all this air up above us, sitting on top of us. And we may think of air as kind of light, we just move through it. But all the air starts adding up, and it's actually quite heavy. And that atmosphere is sitting on us. We don't notice it, you were born into it. It's always been this way. But it turns out the entire atmosphere above you has about 101,325 pascals pushing on you. That is 101,325 newtons per square meter pushing on you all the time. And because we live on Earth and we are somewhat, biased, egocentric, if you will, we have named one atmosphere after Earth's atmosphere. So 1 atmosphere of pressure is the amount of pressure that is on you from Earth's atmosphere, 101,325 pascals. And so sometimes this will be an alternative unit that we will use for pressure. We'll talk about pressure in atmospheres. And I'll have several examples that I work where we travel to different planets, and we'll see how the different pressures from various atmospheres might change things. All right, well, what about that first example I talked about? I said just imagine shoving your hand into a bucket of water, right? Your hand goes into the water moves around your hand. Well, it also actually kind of moves upwards. It gets displaced. So, if water is not contained in a hydraulic system, what happens? Well, it generally flows from high pressure to low pressure, or from a high gravitational potential to a low gravitational potential. Just a fancy way of saying water flows downhill. But water can actually provide a force outside of hydraulics. That is the buoyant force. And it turns out that the buoyant force on an object is equal to the weight of the water displaced. When your hand pushes that water out of the way, well, that water's pushing back on your hand. It wants it up and out of its bucket. And the amount that it's pushing back onto you, the buoyant force on an object, it's equal to the weight of the water displaced. And we know how to compute weight. Weight is just m times g, mass times gravity. But do we usually refer to amounts of water in terms of their mass? Not usually. I don't go to the store and buy a kilogram of water. I usually buy water in terms of volume, gallons or liters. Volume is our more typical way of measuring water. So let's replace that mass with a measure of volume. And mass is actually equal to rho times v. That is the Greek letter for R. It is rho. R-H-O. It kind of looks like a P, but not exactly. You might want to Google an image of this to see how a rho really looks. You kind of just make one motion upwards and then curl under. It's like a very smooth P. No little arrow, no little piece hanging off the upper left tip there. But rho is density, and density is defined as mass divided by volume. So for water, that's about 1,000 kilograms per cubic meter, or on a smaller scale, 1 gram per cubic centimeter. Both of these are the defined densities of water. Anyway, if we put all of this together, the buoyant force, F sub B, is just the weight of the water displaced. Well, weight is mg, and as I said, we're not really going to use m because we rarely know the mass directly of water. We usually refer to water in terms of the amount of volume of water. So replacing m with rho times v, we get the buoyant force is given by rho times v times g. If you get this much water out of the way, capital V amount of water out of the way, it's going to push back with rho times v times g. And I'll give an example of this in terms of a boat floating at the end of the chapter. I believe that is not it for water. So let's turn to the next page. There's a little bit more. Let's talk about pressure underwater. So similarly to the buoyant force, that would be something just displacing a little bit of water. If you keep going further and further underwater, well, there's only so much volume you can displace. But the further down you go, there's more and more water above you. So the further you travel underwater, the greater the pressure is. And you can feel the weight of all that water above you. And this is an equation we might not use, but I figured I would mention it here. But the pressure underwater is equal to density, rho, times g, that's 9.8 meters per second squared, times h, which is your depth, how far underwater you've gone. The further underwater you go, the more pressure you feel. But that's not all. If you were to just plug these numbers in, that isn't the actual pressure you feel when you're underwater, because what's above that water? The atmosphere. There is still air above all that water, pushing down on you as well. And so the total amount of pressure you would feel underwater is P equals rho GH, and then plus 1 atmosphere, or 101,000 pascals roughly, of additional pressure. We have one other equation talking about water. Now, this doesn't really have to do necessarily with pushing on water directly or changing its temperature, but there is sort of a sense of squeezing the water here. And that's that water must follow the equation of continuity. The amount that comes in one side of a pipe better be the same amount that comes out of the pipe. This is almost like conservation of flow. And so I like to look at it this way. It's almost like a wine bottle here that I've drawn, but we've got a big fat pipe that then gets narrowed down into a skinnier pipe. If you have some amount of flow in some big area, it then gets shrunk down to a smaller area, the flow rate increases. I've drawn short, or sorry, not the flow rate, the velocity increases. The flow rate stays the same. I've drawn these arrows short going in to indicate a slow velocity going into the big pipe. When it comes out of the skinny pipe, it has to move faster. It has less area to go through. So you have to squeeze that water out really fast to get the same amount out as you're putting in. And this is easier to understand when we look at the units. So what's true about this situation is that the area times the velocity on one side better equal the area times the velocity on the other side. And looking at the units, this makes a little more sense. If we look at the units of A times V, we get units for area, meters squared, times units for velocity, meters per second. That gives us cubic meters per second, which is a measure of volume over time. It's how much, physically, how much water, like I said, volume is the typical way we measure water. However much water goes in one side, better be the amount of water that comes out the other side. And we'll probably be using cubic meters per second in this equation, but out in the real world, you might see this as something like gallons per minute listed on, say, a pressure washer. And I often refer to this as the pressure washer equation because that's one of the most common ways in which it sort of naturally arises. And this is the last topic for this video, but I will pause and give you guys an extra little tidbit. Because this equation uses areas, I want to pause and talk about areas. Because you're going to have to compute that area. I might not always just say the area is, 10 square centimeters. I might say something about the radius or the diameter. And you need to compute the area. And there's only two simple ones I would ask of you. The area of a circle is pi times r squared. And remember, that's an r. Some of the problems give you a diameter, which needs to be divided by 2 to become a radius. And then the area of a square. An area of a square is just side squared. I'm not going to ask you weird areas. I will commonly give you the areas, but it is also perfectly fair for me to ask you to compute an area given a radius or a diameter. Circles are very common. We're going to see a lot of circular pipes, a lot of circular pistons for the hydraulic equation. But I'm not going to ask you guys to do any complicated area calculations. However, these you should know and have memorized. Write them on your equation sheets if you want to. But all right, well, that's the second part of Chapter 9. This is how liquids behave whenever you push on them or squeeze them. We'll finish this chapter off with gases in a moment.